Hello, this is Xiangli from Stony Brook University. Today, I'm glad to present our work, Crossway Diffusion, improving diffusion-based visual motor policy via self-supervised learning. The diffusion model has shown its great potential in multiple computer vision and robotics tasks. For example, diffusion policy takes advantage of an action diffusion model. For each inference, it iteratively denoys the action sequence conditioned on the observation. It achieves promising results on multiple behavioral cloning tasks. At the same time, self-supervised learning objectives are known to be effective for visual representation learning, which can eventually benefit visual motor policy learning. So in this paper, we investigate the problem of whether the diffusion-based visual motor policy will benefit from the additional auxiliary self-supervised objectives. And we are happy to announce that the answer is yes. So let's start from the basics first. The existing diffusion policy model contains a state encoder that extracts useful information from the input states. An action encoder and decoder take the noisy action sequence and the input state features and generate a relatively denoised action sequence. The training objective of the diffusion policy is a single DDPM loss. Starting from here, we propose our method Crossway Diffusion, a simple yet effective way to improve diffusion policy via state reconstruction. Crossway Diffusion extends the existing framework of diffusion policy by introducing a state decoder and a state reconstruction objective. The state decoder is designed to reconstruct the original input states from the intermediate representation of the denoising network during training. While in the evaluation stage, the state decoder will be discarded without introducing additional computational costs. The reconstruction objective here is a simple mean squared error between the predicted states and the input states. So as you can imagine, during training, there are two flows intersecting in this model, changing information. And that's why we name our method Crossway Diffusion. By doing so, we explicitly regularize the diffusion model to capture the useful information from both the action sequence and the input state. To achieve best performance, both visual and numerical states are predicted in this reconstruction decoder. The final training objective of Crossway Diffusion is a simple weighted sum of the diffusion loss and state reconstruction loss. And this actually is a core idea of the Crossway Diffusion, very simple but effective method. So following the literature, we evaluate our method with other competitive baselines on 10 simulated datasets. In addition, we collect 2 real-world robot manipulation datasets and perform corresponding evaluations. Experiments on simulated datasets show that our method consistently achieve better performance over the baselines. Especially on this challenging dataset, transport MH, our method significantly outperforms the diffusion policy baseline by 60%, and we have variance even performs better. Similarly, in the real-world experiments, our method achieves better performance. And besides that, we observe that our method is robust to many visual distractions and many unseen scenarios. For more demo videos, please check our project page at the end of this video. We further conduct ablation studies on multiple design choices regarding the state decoder and multiple auxiliary objectives. In these experiments, we compare the different ways to take the intermediate representation for state reconstruction. The results show that all 3 designs are consistently better than the diffusion policy baseline, and our method is robust to multiple designs. We also conduct experiments with different state decoder architecture, including a Bayesian transformer variant. Our default setting achieves better performance in most cases. Finally, we explore the effect of different auxiliary objectives. In this group of experiments, we push the model to predict the future states instead of reconstructing the current state. And it turns out that reconstruction is the most effective method in most cases. We further test other cases where only visual observations are reconstructed and use a contrastive objective instead of a reconstruction objective. And the conclusion is that not all self-supervised learning objectives will benefit policy learning, while the proposed reconstruction objective can consistently improve diffusion-based policy. We also show that our method can generate reasonable reconstructed images. For more experiments and examples, please refer to our paper. So in conclusion, in this paper, we explore multiple self-supervised learning objectives to improve diffusion-based visual motor policy learning. And we found that Crossway diffusion can consistently improve the baseline with a simple reconstruction objective and a state decoder. We conduct detailed experiments and applications, and we hope our work will inspire future study on self-supervised learning for diffusion-based policy learning. Our code, dataset, and pre-trained models are available at the link here. Thank you for watching.